I would like to thank to the organizers for giving me an opportunity to be here. I will talk about new characterization-based exponentiality tests, and a significant part of my talk will be dedicated to comparison of Bahadur efficiency of some tests. My presentation will be separated in 4 parts. First, I will give some introduction about goodness of fit tests. Then I will talk about new tests for exponential distribution. Then about assessment of the quality, mostly about Bahadur efficiency. And at the end, I will give some conclusions. The exponential distribution is one of the most widely studied distribution in theoretical and applied statistics, and many models assume exponentiality of the data. Because of that, it is important to have some battery of powerful tests for that distribution. This distribution appears in survival analysis, reliability theory, stochastic processes, and many other domains. If we want to test composite hypothesis of exponentiality, then null hypothesis is that data belongs to a family of exponential distribution with some unknown parameter lambda. A large number of different goodness of fit tests for the exponential distribution have been proposed in literature. And I will give just a brief review of some mostly uses approaches. First one is classical approach, meaning that we use goodness of fit test based on empirical distribution function applied on a case of exponential distribution. Such tests are Kolmogorov-Smirnov, Kramer-von Mises, and Anderson-Darling tests. And those tests with Lilliefors modification can be applied on for testing a composite hypothesis. Second approach is to use tailor-made tests for exponential distribution. Those tests imply some properties of exponential distribution, such as different integral transforms, for example, Laplace transform or characteristic function, then maximal correlation, entropy, etc. Some papers in which those type of tests were constructed are presented here. In last years, especially in last year, characterization-based approach became popular. And there are a lot of different characterization-based tests. Characterizations are properties which only one particular family of distribution has. They, through simple properties, we can, if we include a characterization theorem in test statistic, then we can easily have appropriate distribution to check is that distribution is true. Especially suitable type of characterization for constructing of goodness of fit test is equidistributional type characterization. Bojan already said something about that. Equidistributional type characterization we can define as if we have two homogeneous function omega 1 and omega 2 which depend on m independent and identically distributed random variables, and if these two functions are equally distributed, then distribution of this sample is some particular distribution. In our case, that is exponential distribution. Equality in distribution, as Ben already said, is can be interpreted in different ways as equality in density function, equality in distribution function, or equality in some integral transforms. And because of that, we can construct a lot of different tests based only on one characterization. Here are presented some characterizations of exponential distribution. For our test, we used Puri, Rubin, and Dessous characterization, but later I will present some tests in which are based on these four characterizations. Now I will talk about new tests. Our new tests were constructed as L2 or L infinity difference, a transformation of difference between two V empirical transforms. We used two transforms. First one is V empirical distribution function, and second one is empirical Laplace transform of random variable from the characterization. First test statistic is constructed as L2 transformation of difference between two V empirical distribution functions. Second class of statistics is constructed as L2 transformation of the difference between two V empirical Laplace transforms. And the last one is constructed as L infinity transformation of that difference. In second and third class, you can see that there is weight function. On the next slides, I will use one particular weight function, and I will explain why we use exactly that one. First test statistic, after some calculation, it can be seen that it is actually some V statistic with kernel of order 2 times m plus 1. It is easy to see that first projection of this kernel is equal to 0. And that's after some calculation, it can be seen that second projection of this kernel is not equal to 0, meaning that this statistic is actually weakly degenerate V statistic. Also, this statistic is scaled free, which gives us opportunity to test composite hypothesis with this test statistic. And also, the large values of this test statistics goes in favor of alternative distribution. The limiting result for this statistic under the null hypothesis can be obtained from well-known theorem for weakly degenerate V statistic. And it can be seen that our test statistic converges in distribution to linear combination of his squared random variables, where these coefficients are eigenvalues of the integral operator A, defined like this, and where phi2 is second projection of the kernel. This explicit values of these eigenvalues is often hard to obtain, and later I will give some approximation method for obtaining of these values. For the second class of test statistic, first we can see that weight function is this exponential function. Actually, there is two reasons why we use this weight function. First is simplicity of calculation, and second is based on Tuberian theorems. In that theorems are proven that the behavior of distribution defined on positive part of real line is reflected by its behavior of its Laplace transforms near 0 and vice versa. Since that, if we choose small value of A, then this function decays slowly, which should give us good power results against alternative with infinite density at 0. On the other hand, if we have a large value of A, then this weight function puts most of its mass near 0, which should give us good power performance of tests against alternatives with great difference from exponential distribution in tail behavior. Because of that, we can choose appropriate value of A for some alternatives. After some calculation, it can be seen that this is actually V statistic of order 2 times m. But you can see that here is estimation of the parameter. The role of this estimation is to make this statistic scale free under the null hypothesis. And then we can test composite hypothesis with this statistic.
What is G?
G is defined here.
Okay, it is defined, but where it arises?
Here. This is G.
Okay.
This function here.
Okay.
Okay. Similar as before, large values of test statistic goes in favor of alternative distribution. The problem for obtaining a limiting distribution of this statistic is actually this estimation here. And before I proceed to limiting distribution of this special statistic, I will give some general result for weakly degenerate V statistic with estimated parameter. Actually, we have this V statistic with estimation of the parameter of order 2 times n with presented kernel. We will see later that a lot of different test statistic actually has this form. Here, function g is some function and m is finite measure. For obtaining asymptotic properties of this statistic, we need to define auxiliary statistic. Actually, this statistic is obtained with Taylor expansion of function g. And also, we need to suppose that estimation have this expression actually is some linear function. The impact of the estimation is presented here actually and here. We've proven that under this condition of linearity from the previous slide and some conditions of smoothness of function g, which I omit here, these two test statistics has actually same limiting behavior. And second result is that if we know that this statistic V star is weakly degenerate, we can obtain its limiting distribution from the previous theorem. And then we know the limiting distribution of our test statistic actually is the same as for V star. It's a linear combination of chi-squared random variables, where these eigenvalues are related to operator defined based on second projection of the kernel of statistic V star. Actually, this function mu, if we return to previous slide, this function mu is expectation of this function g. If this derivative is equal to 0, then there is this term here is equal to 0 and here 2. And in that case, there is no impact of the estimation of the parameter to the limiting distribution. And this statistic V star will be the same statistic as statistic V, but with true value of the parameter, and that is the easier case. Actually, that is the case for our test statistic. This function mu is 0 for our test statistic because we constructed our test statistic based on characterization. and this function here will have expectation equal to 0 under the null hypothesis. And because of that, there is no impact of estimation of the parameter on limiting distribution of our test statistic, and this result can be a little bit easier obtained a little bit easier than that general result. And we obtain that our test statistic converges in distribution to linear combination of chi-squared random variables under the null hypothesis. And these eigenvalues are related to second projection of kernel, actually our kernel, with true value of the parameter. We also proved the theorem about limiting behavior of our test statistic under the alternative distribution. And in that case, our test statistic is not anymore weakly degenerate, and it has a limiting normal distribution with presented parameters. And for the third class of test statistics, this is actually a supremum of absolute value of some V empirical process. The estimation of the parameter is presented to make this statistic scale-free under the null hypothesis. A limiting distribution is presented in this theorem and this corollary. First, we proved that this process converges weakly to centered Gaussian process with presented covariance function. And then, as a consequence, we have that our test statistic converges in distribution to supremum of absolute value of that process. I didn't say, but again, the large values of test statistic goes in favor of alternative distribution, similar as before. Now I will talk about assessment of the quality of the tests. Usually it is used asymptotic. First way to assess the quality is to use asymptotic efficiency for large sample sizes, and second way is to use power study for small and moderate sample sizes. The ordering of tests is not necessarily the same when we use these two criteria, and because of that, it's desirable to consider both criteria. I will mostly talk about asymptotic efficiency, and for power performance, I will give just the results for new tests. If we have two sequences of test statistics with the same null and alternative distribution, relative efficiency is defined as ratio of sample sizes needed to reach the same test power. As we can see, this value depends on three parameters: significant level, power, and parameter of distribution. And it's usually hard to obtain this value. One way to make this simpler is to use asymptotic relative efficiency. If significant level tends to 0, then we have Bahadur asymptotic relative efficiency. If power tends to 1, then we have Hodges-Lehmann asymptotic relative efficiency. And if parameter tend to parameter of null distribution, then we have Pitman asymptotic relative efficiency. Bahadur asymptotic relative for Bahadur asymptotic relative efficiency, we don't need to have asymptotic normal distribution as asymptotic distribution of test statistic, and because of that, we use this type of relative efficiency. It is proven that Bahadur efficiency can be obtained as a ratio of the Bahadur exact slopes of these test statistics. But for obtaining the Bahadur exact slope, we need the large deviation function, which is also usually hard to obtain. And mostly tests are compared using approximate Bahadur asymptotic relative efficiency, actually the approximate Bahadur slope. For obtaining approximate Bahadur slope, we need to know the limiting distribution of test statistic, and it is necessary to not be a degenerate distribution function. Then the logarithmic tail behavior need to have this expression, and limit in probability of test statistic need to exist for parameter of alternative distribution. And then approximate Bahadur slope is equal to product of this constant A for second point and square of function B. Locally, approximate Bahadur slope is equivalent to the exact Bahadur slope, and in that case we can use it for obtaining approximate Bahadur relative efficiency. Locally means that alternative distribution is near to the null distribution, which is the most important case. Since our test statistics are actually V statistic or some function of V empirical process, I will give some results for local Bahadur slope of V statistics. First, it is considered local case. Because of that, it is defined some function g of alternative distribution. Distribution such that theta is equal to 0 only in the case of null distribution. And also, it is necessary to some regulatory conditions to be satisfied. First one is consistency of statistic, and second and third are related to some integrability of derivatives of density of alternative distribution. Also, we assume that the kernel of V statistic is bounded. In non-degenerate case, under the conditions 1 and 2, exact Bahadur slope can be obtained from this formula, where function b is defined in first condition, m is order of statistic, and sigma 1 square is variance of first projection. In degenerate case, under conditions 1, 2, and 3, the formula is presented here. Delta 1 is the largest eigenvalue of the integral operator A defined earlier. We proved that under some conditions, the approximate, for the statistic with estimation of the parameter, approximate slopes have the same expressions as these exact slopes. Which formula we use depend on the case. Is this non-degenerate or degenerate case? And actually depend on limiting distribution of test statistic. Because of that, we classified tests into 3 groups according to their limiting distribution. First group is made of test statistic with normal asymptotic distribution. Second group are made of test statistic with an infinite linear combination of ID chi-squared random variables as asymptotic distribution. And third group are test which limits distribution coincide with the supremum of some centered Gaussian process. For each of these three groups, I will present some tests which belongs to that group, and then I will give some theorems from which we can obtain the approximate Bahadur slope. First group are made of non-degenerate V statistic with some kernel phi of order m. Its asymptotic distribution is normal, and that can be obtained from one of these two papers. First one is Havding, and it's for statistic without estimation of the parameter, and second one is for the test statistic with estimation of the parameters. Here are presented some well-known exponentiality tests, Epspuli, Koksakis, Galgastrovic, and Moran test, and one newly test from 2016, Bojana already presented. This is integral transformation of difference between two V empirical Laplace transforms, and I will later consider this test in for two particular characterization, Dessous and Puri-Rubin characterization. Also in these groups, in this group are the tests constructed as integral transforms of difference between two V empirical distribution functions. Here are presented 6 different tests, actually 6 different characterizations which are the basis of those tests. For each of these tests, approximate Bahadur slope can be obtained from one of these two formulas. We suppose that density of alternative distribution belongs to class G. And for statistic without estimation of the parameter, the expression is presented here, where phi is first projection of the kernel, and sigma square is variance of first projection. For statistic with estimation of the parameter, the expression have two terms. Phi star is first projection of the kernel capital Phi star, which can be obtained in the similar way as this Phi star from the second theorem, and this is variance of that first projection. If estimation of the parameter doesn't have impact to the limiting distribution, then this term is equal to 0, and these two expressions will be the same. In the second group are weakly degenerate V statistics with some kernel phi. The statistic which we are considered have one of these two forms. First variant is without estimation of the parameter. Second variant is with estimation of the parameter. As we already see, the limiting distribution is infinite linear combination of ID His squared random variables, and of course our two classes are belongs to this group. Here are presented the formulas for two particular characterizations, Puri-Rubin and Dessous characterization. In this group are also Lilliefors modification of Kramer-von Mises test, Lilliefors modification of Anderson-Darling test, and some tests based on constructed as L2 transformation of some characterizations related to Laplace transform or characteristic function of exponential distribution. For all presented tests, the approximate Bahadur slope can be obtained from one of these two formulas. First one is for statistic without estimation of the parameter. Phi2 is second projection of the kernel. Delta 1 is the largest eigenvalue of the operator A from first theorem. And in the second case, delta 1 star is the largest eigenvalue of the integral operator A star from the second theorem. If estimation of the parameter doesn't have impact on the limiting distribution, then these two terms are equal to 0, and these two expressions will have the same, will be the same. In both cases, this delta 1 and delta 1 star is mostly unknown. And I said at the beginning that I will give some approximate method for obtaining of largest eigenvalue. Here is presented the method proposed in Božin with co-authors in 2018. First, we need to symmetrize our operator A in this way. And this operator has the same spectrum as operator A. Then we need to truncate it on the set of real functions with support on interval 0 to b, like this. And for sufficient large b, the operator t and a differ on a set of negligible mesh. On the other hand, we defined a symmetric linear operator defined by matrices with these elements, and the operators t and m are symmetric and self-adjoint, and the norm of their difference tends to 0 as m tend to infinity. Therefore, the sequence of the largest eigenvalues of operator m converges to the largest eigenvalue of operator t, and when b tends to infinity, then this eigenvalue converges to eigenvalue of our operator. The similar is for operator A star. Based on this, we can obtain the largest eigenvalue of the operator. And third group is made of supremum of non-degenerate V empirical processes with some kernel phi of order m. Asymptotic distribution is supremum of some centered Gaussian process. Our third class of test statistics belongs to this group, and here is presented two variants of our test statistic for two characterizations. Also, in this group are Lilly force modification of Kolmogorov-Smirnov test and test constructed as supremum of absolute difference between two V empirical distribution functions. And these tests are actually constructed based on same characterization as in first group. The local Bahadur approximate slope can be obtained from these two formulas for all tests present earlier. First is for statistic without estimation of the parameter, where this k is appropriate covariance function. And second is for statistic with estimation of the parameter, where this k is covariance function related to phi star. If estimation of the parameter doesn't have impact on the limiting distribution, then this term here is equal to 0, and we will have the same expressions. When we want to compare some tests from Bahadur efficiency perspective, it will be convenient to have some upper bound. From Bahadur-Ragavachari inequality, it is known that exact Bahadur slope is always less than double Kullback-Leibler distance between null and alternative distribution. But for approximate slope, there is no such upper bound. Mostly, the approximate Bahadur slope is compared with approximate Bahadur slope of likelihood ratio tests, which is known to be locally optimal parametric tests. In very general conditions, the exact Bahadur slope of likelihood ratio test is equivalent to the double Kullback-Leibler distance. And because of that, we can define absolute local approximate Bahadur efficiency as ratio of the approximate Bahadur slope of some test and approximate Bahadur slope of likelihood ratio test in local case. This value will have, this will be between 0 and 1, which is more convenient for comparison. Here is presented double Kullback-Leibler distance between some alternative from class G and exponential distribution. For alternative distribution and comparison purpose, we use these four alternatives: Weibull distribution, gamma, linear failure rate, and mixture of exponential distribution with negative weights. All of them belongs to a family G. Results are presented on the graphics. Here are the results for Weibull alternative. On the graphics are local approximate Bahadur efficiencies with respect to likelihood ratio tests as a function of tuning parameter A. For those test statistics which don't depend on tuning parameter, efficiencies are presented as straight lines. First, we can see that in third, tests are separated as previous in three groups. In third group, we can see that new tests are more significantly more efficient than other tests from this group, and this conclusion will be the same for three other alternatives. We will see that later. Also, it can be noticed that other tests based on L infinity difference are least efficient if we compare all tests. In first group, for this alternative, we can see that Coxsacki's test and Moran test are the most efficient tests, but those tests are known to be locally optimal for Weibull and gamma alternative, and that is expected result. In second group, for appropriate value of A, a lot of different test statistics have large efficiency. This is here are the results for our test statistic, which are the optimal. For gamma alternative, the results are very similar as before. For linear failure rate alternative, the most efficient tests are EPS-PULI and two tests labeled with HM1 and HM2. It is interesting that these two tests labeled with HM1 and 2 are less efficient for all others alternatives. In case of fourth alternative distribution, most of tests from second group are very efficient for appropriate value of parameter A. In general, we can say that there is no uniformly most efficient test because that depends on alternative distribution, but that our tests are between most efficient tests. For power study, we conduct power study in small and medium sample sizes, 20 and 50, and for significant level of 5%. The results are presented here for small sample size. for second and third class, we use some values of parameter A. For tests labeled with M, A is 0.5, 1, 2, and 5. And for tests labeled with L, A is 0, 0.5, 1, 2, and 5. We can see that all tests are well calibrated since the sizes of tests are 5%. And we can see that powers are moderate to, in most cases, have moderate to large values. If we compare these three types of tests, we can see that tests based on V empirical distribution function are less powerful than other tests. And also, if we compare tests M and L, we can say that some test is the best because that depends on alternative distribution, value of parameter A, and on characterization. If we increase sample size, then the conclusions are very similar, but the values are larger, which we are expected. And some conclusions, actually, some review of my talk. We proposed some new classes of test statistics, which are scale-free goodness of fit tests, highly efficient in terms of absolute local approximate Bahadur efficiency, and among the most powerful exponentiality tests. If we compare these results with some other results, we can see that these powers are higher or very similar to the powers of some other exponentiality tests. But I didn't present that here. Also, we proved the theorem about asymptotic properties of weakly degenerate V statistic with estimated parameter, and we conducted an extensive comparison of different recent and classical exponentiality tests from Bahadur efficiency perspective. Our current and future work, as Bojan already talked about that, we work now with sensor data and adaptation of these tests. Our plan is to obtain Bahadur efficiency in that case. Also, we want to form some R package with all characterization-based exponentiality tests to make them more available to other people. And this procedure can be applied on some other distributions in the similar way. And here are some references for my talk. Thank you.